All right, this is the second part of section 10.1. In 10.1, in the first part of 10.1, we discussed the confidence intervals, or creating and interpreting confidence intervals for the difference in population proportions. But here we're going to talk about, in the second half of this section, we'll talk about doing hypothesis testing or significance testing for the difference in population proportion. So again, remember, this means we're going to take two different samples from two different independent populations, and then we're going to test whether or not we think the true proportions differ by a certain value, based on whether the sample proportions, the p hats, differed by a certain value. All right, so an observed difference between two sample proportions, that's two p hats, can reflect an actual difference in the parameters, the actual difference in P1 minus P2. Okay, so the difference in p hats might reflect an actual difference in those parameters, or it may just, that difference that we see in the p hats may be just due to chance variation in random sampling, all right? Or perhaps random assignment if we do an experiment. So the significance test that we're going to do now is going to help us decide which explanation is more likely valid. All right, so the null hypothesis is going to be that P1 minus P2 equals some hypothesized value. Now, we're going to restrict ourselves here in this class to that hypothesized difference being 0. So in other words, we will say that there is not a difference between P1 and P2, the true population proportion from population 1 and the true population proportion from population 2 is the same. So our null hypothesis is essentially there's no difference between the two parameters. All right, so we will write the null hypothesis is P1, P subscript 1 minus P subscript 2 is equal to 0. Now, you could also say, instead of saying that, that they're equal. So you could say as an alternative, not alternative hypothesis, but an alternative way of writing the null hypothesis is that P1 is equal to P2. And that is kind of more akin to what our calculator method sort of is. But we our book tends to use P1 minus P2 is equal to 0. And then as the alternative hypothesis, then we will say, three options, of course, depending on whether it's a two-sided or one-sided test. The alternative is that P1 minus P2 is not equal to 0, P1 minus P2 is less than 0, P1 minus P2 is greater than 0. And then again, there is a benefit to writing it the other way, because that's really how our TI-84 sort of uses it. When you have to choose the alternative hypothesis in the calculator, they tend to write it in this way. Instead of the difference being equal to 0, they'll tend to say P1 not equal to P2, P1 is less than P2, or P1 is greater than P2. It just takes a little bit of algebra, right? I mean, you take this equation, this inequality, for example, and you add P2 to both sides, and you get this one down here. So they're mathematically equivalent to each other, but just one is kind of how we say it in our book, but one is more useful for being able to select the correct alternative hypothesis when we do the test in our TI-84. All right, the conditions that we have to check here, very similar to the ones that we saw in for the confidence interval. So first thing is we have to have the data from two independent random samples or two groups in a randomized experiment. Make sure that if they're randomly sampling, that you're talking about plural. Don't say data is random. That won't be good enough when you're talking about random. So you want to talk about two separate random samples from two different populations. The 10%, you have to check the 10% that we're not, each sample is less than 10% of its related population. And then large counts. In this case, we don't we don't have uh, we don't have a p not a hypothesized p value individually. Like we know that the difference of the two p values will be 0, but we don't have like a hypothesized p value for p1 or p2. So we can't really use p naughts here like we did when we were dealing with one sample. Here with two samples, we are stuck using the p hats rather than any p naughts there. Because again, we know that we're hypothesizing the difference in p1 and p2 is 0, but we don't have the individual values of p naught to place in these. So we use the p hats here. Okay. The statistic we use here, the Z statistic, is going to be used because the sampling distribution of the difference in p hats is going to be normally distributed. The statistic is simply the difference in p hats. Again, the hypothesized difference for us is always going to be 0. So that's why we just go ahead and put the 0 in there, or we really can almost just forget about that in the formula. The standard deviation of the sampling distribution of the difference in p hats is a rather complicated formula in this case. So that bottom denominator we have to talk about. All right. If the null hypothesis is true, and either P1 minus P2 is equal to 0 or P1 is equal to P2, if that is true, then we're saying that the two parameters are really the same. And we call their common value just P. So we can think about that. And so we want to estimate. So they're the same, and we want a way of sort of estimating that. And so it kind of makes sense to pool the data from the two samples. And so we call this a pooled p hat or pooled sample proportion. And so it is the total number of successes in both combined samples divided by the total number in both samples. So we call this a p hat with a subscript c for combined, but often we'll refer to this as the pooled p hat. I guess it would look kind of funny if we did p hat sub p with a subscript p, pp. That would be kind of weird. So we use a subscript c, but we'll often think of this as the pooled p hat. And so that's really just the number of successes in both samples added up, and then the two sample sizes added up. And so we now, like, remember, we're pretending like the null hypothesis is true. And so since the proportions are the same, the p hat that we get should be the pooled p hat, and that will be x1 plus x2 divided by n1 plus n2. So think of it this way. We are hypothesizing that the two population proportions, P1 and P2, are equal. So this means that we can really treat them as one population. And as a result, the two samples we took, we can think of them as sort of being one sample. We might want to ask if the population, if the proportion of U.S. adults who use Twitter differs from the proportion of U.S. teenagers who use Twitter. And an SRS of adults and an SRS of teenagers are surveyed. And we have this two-way table. And so what would be the p hat for adults? Well, it's just these two numbers, right, as a fraction. And then what is the p hat for teenagers? It would just be these two numbers. But what would be the pooled p hat? The pooled p hat would be the sum of both of those rows and so the summed p hat, we don't take and add the p hat sub a and p hat sub t. Instead, we pool it using our formula from the last slide. All right, now this complicates things a little bit. And this is the formula for the z-score or the z-statistic in this 2-sample z-test for the difference in p's. So you can see why it's really probably important that we start using our calculators for these things. For the do portion of our 4-step process, we really want to not have to plug everything into this calculator, into this formula, and use our calculators to try to calculate that, because it's very accident prone. So we really want to be able to just do this using our test in our calculator. Now this formula on the right, the one on the left kind of makes sense because it's it's pooled p hat. So in the bottom formula, where we have this standard deviation of the sampling distribution, we really aren't going to use p hat sub 1, p hat sub 1, p hat sub 2, p hat sub 2. We're going to use the combined or pooled p hats. So what we've done is we've factored this stuff out in front, did a little algebra. And so the reason I'm including this formula in the blue is because that's the formula that's on our formula sheet, so that if you were to have to ever do this by hand, you should be comfortable with that. So the one in the blue is what's on our formula sheet. All right. But again, hopefully you won't be using this very much. You're going to use your calculator to do the do portion of this. And again, we have either a one-sided test for the difference being greater than 0, the difference being less than 0, again, would be a one-sided, and then not equal to, we have, just like we've seen before, this would be a two-sided test. All right, let's look at an example. Are teenagers going deaf? In a study of 3,000 randomly selected teenagers between the years of 1988 and 1984, 15% showed some hearing loss. In a similar study of 1,800 teenagers in the years 2005 to 2006, 19% showed some hearing loss. All right, the question is, do these data provide convincing evidence that the proportion of all teenagers with hearing loss has increased? So has the hearing loss increased over time? So we see the percentages have increased, but is that just by chance alone, or is that because the hearing loss has actually increased? So what we want to look at is the state. So start with the state. Now, this gets pretty complicated when we're dealing with these differences. And so you have to set up your null hypothesis. That's pretty easy, right? That the difference in the two true proportions is equal to 0. But the alternative, so before we actually write this alternative, it's probably good to sit down and think about what you're calling P sub 1 and P sub 2. Now, the calculator kind of tends to put things as P1 minus P2, or P1 is equal to P2. And so what I tend to do is try to leave P1 minus P2 in the formula. And then I adjust which thing I call P1 and which one I call P2. It ultimately doesn't matter, but you have to be super consistent. If you flip this around in the middle of your test, it's going to cause problems. So what I've decided to do here is to call P2 the earlier time frame. So 2 is the 1988 to 1994 test, the results. That's not the results, but that's the time frame in which we were talking about the true proportion, P2. P1 is the later time. Probably makes almost more sense to reverse that, but just believe me that we want P1 minus P2 And once you set that up the way I've done it, then the alternative can only come out one way. So think about what you want your alternative to be. What does it mean for there to be an increase? Remember, the thinking is that, or the suspicion is that hearing loss has increased among teenagers in the later years. So nowadays, teenagers have more hearing loss. So what would you think that alternative hypothesis should be? All right, so it really should be P1 minus P2 is greater than 0. If P1 is greater, because it's the later time frame, then that means that hearing loss has increased. Now, if you reverse those, that's fine. Then you have to have less than 0. So it's really, you got to be really careful and set that up properly. Once you set up your state, your null hypothesis, state what your P sub 1 is and what your P sub 2 is, and you set up your alternative correctly from that, then everything else has got to be the same. You've got to keep everything consistent. All right, so now our plan. So what is our inference procedure? And check your 3 conditions. So pause the video, write that out. All right, so your plan, we're doing a 2-sample z-test for difference in p's. You can actually write diff of p's if you want, or p sub 1 minus p sub 2. And again, makes sense to just keep that consistent. SRSs for both studies were done. So, notice I'm doing plural there. 3,000 and 1,800 are both less than 10% of the teenagers that were evolved. So those were the sample amounts in both studies, and we can assume that those are less than 10% of all teenagers. So there were more than 30,000 in the one time frame and more than 18,000 in the other time frame. All right, and large count conditions, be careful. Make sure that you're using your p hat sub 1 as the right one and p hat sub 2 as the right one from the studies up above. You can see all of those are greater than 10. So we know our sampling distribution of the difference in p hats will be approximately normal. All right, I cheated a little bit and didn't write that statement in there because of time, of space concerns. I wouldn't be able to fit all the rest of it on one slide. All right, now we want to do our do. So you could do it by hand, and I'm going to show you what it would look like doing by hand, but I really suggest that you're doing this on your calculator. So you want to pick the right values in your calculator. So first of all, I did it by hand here. And actually, the p-value is so low that it doesn't actually show up on our table, but our table, we know it's really small, so it's 0.0002. It's actually less than that, but our table doesn't go down that far. All right, and then if you do our calculator, we want to... Our calculator, we're going to use a 2-prop z-test. So 2-proportion z-test is what our calculator calls it. And I would list down what the inputs are. And those inputs are how many successes were in sample 1 and sample size 1. Remember, sample size 1 in this case is the later time frame study in 2005 and 2005 and 2006. And then X sub 2, that is the number of successes, or for us, success is hearing loss. And then the sample size for the second sample, which is really the first sample, all right? But we're calling it 2 just to be consistent as we go through the whole problem. If you flip those around, then you're going to be on the wrong side of your normal curve, and you're more than likely to get this wrong. And then the one other thing you have to do is, even though I wrote the alternative hypothesis as P1 minus P2 For the calculator, we really want to think of it as P1 is greater than P2 in the alternative, because that's going to allow us to pick the right alternative hypothesis in your calculator. So make sure that you're keeping, again, your what's P1 and what's P2, which one's which. That's really important. All right, and then from our calculators, we want to record the z-score, the z-statistic, and the p-value. All right, and so finally, we want to finish with our conclusion. Remember, we're going to compare our p-value to our alpha. The conclusion really is the same, regardless of what test we're doing. Every test is done the same. We now have a p-value, so compare your p-value to your alpha, decide whether you're going to reject or fail to reject, and then write your alternative. Do you have convincing evidence to support the alternative hypothesis? So pause the video and write that out. All right, so your conclusion. Because the p-value of, and I rounded it to 0.00003, is less than our alpha of 0.05, we will reject H naught. And now we have convincing, or because our p-value is so small, we might even say we have strong convincing evidence that the proportion of all teenagers with hearing loss has increased. So the p-value is so small that that difference that we saw up here, it could probably not occur just by chance alone, right? It's more likely that there's an actual difference, that there has been an increase in the hearing loss over those years. All right, so part B says, between the two studies, Apple introduced iPods. If the results of this test are statistically significant, and they were, can we blame iPods for this increased hearing loss in teenagers? And I think the answer is no. And we know that in order to show causation, we have to have some sort of experimentation, right? We would have to have a controlled, some people get exposed to iPods, some people don't. We would have to have some sort of experiment to show causation. And this is not. This was from two different surveys from two different years. Other things are going on as well. And so as a result, we couldn't just do that. You know, people listen to music more now than they did before. Headphones in general, right? Not necessarily iPods, but could be other factors that are also occurring at the same time over that time frame. All right, some inferences, some things to take note of about inference when we're doing experiments. Many important statistical results come from randomized comparative experiments. The comparative meaning we have more than one treatment group. Often one of those treatment groups is a control. Defining the parameters in experimental settings is a little bit more challenging. All right, most experiments on people use recruited volunteers as subjects. So we're not sampling people. We use volunteers that would for the subjects. When subjects are not randomly selected, researchers cannot generalize the results of the experiment to the larger population. So remember, we did this back when we were talking about experimental design versus surveys. And so if we don't randomly select people, and we generally don't, right? I mean, most times we have to use volunteers. So we're limited to what we can infer back to, the greater population. We have some limited inference there. So researchers can draw a cause and effect, but we can only say, well, this result, cause and effect, seems like a true cause and effect relationship in people like those that were in our study, but not in our experimental study, but not the general population. Okay, it has to be people In order to go back to the general population, we have to have sampled those people for the experiment from the general population, and you just can't do that, generally speaking. Unless the experimental units were randomly selected, we don't need to check our 10% condition when we're doing inference about an experiment. So that means our 10% condition, if we're running an experiment and we're doing our 4-step process, then we don't have to check the 10% condition when we're not sampling. All right. When we use volunteers, we don't have to, we randomize because we randomly place them into different treatment groups, but we didn't sample without replacement, so we don't have to check our 10% condition. All right, so we have our homework. We have some 4-steppers in there. We have 16, 18, and 21 are 4-step problems. So make sure that when you're doing this homework assignment, you're including 4 steps for those 3 problems. And this homework is due next class.